The force production by the skeletal muscle depends on two factors, neural factor as well as the skeletal muscle factor. Okay, so as well as skeletal. The neural factor is the one where how much stimulation is provided by the axon. So based on that, so that determines the force of contraction. Okay. And the skeletal factors, it includes the mechanical properties of the skeletal muscle as well as the architecture of the skeletal muscle and its mechanical properties. Okay, so both are interdependent. Yeah, so the architecture also determines the mechanical property of the skeletal muscles. So what we'll do is first we'll look at the neural component which determines the muscle mechanics. Okay, so number one, neural component, graded muscle response. See how the muscle responds when two neural stimuli are provided, then your graded muscle response occur. So you know that, right? When you give a stimulus, action potential sets in the nerve, then translated to the end plate potential, then it reaches the muscle, again action potential traverses along the muscle fiber, and then contraction occurs. Okay, excitation contraction coupling. So this is what is excitation contraction coupling. So how does this happen? So graded muscle response. So to understand this, you need to have two important factors. One is twitch response, the other one is tetanus. You must have heard, right? Twitch and tetanus. So twitch means what? When a muscle responds to a single stimuli. Okay, so basically twitch is nothing but a rapid quick contraction of a muscle. Okay, like a rapid contraction of a muscle which responds to a single stimuli. Okay, and tetanus, it responds to multiple stimuli, 2 or 3 stimuli. When it stimulates the muscle fiber, that is called as the tetanus. The twitch response has three phases. One is the latent phase. Okay. Second one is the contraction phase, and the third one is the relaxation phase or the refractory phase. So the latent phase, and then the contraction phase. Okay, and then finally the relaxation phase or the refractory phase. Okay, so before this you have a resting membrane potential here, you have a threshold potential. That means your potential should reach the threshold, then the muscle starts contracting. Yeah. So while contracting, what happens is there is a phase called a latent phase. So latent phase in a twitch is nothing but where the actin and the myosin bind with each other. That is a latent phase. Okay. Contraction phase is when the power stroke occurs. After binding, the power stroke occurs, right? How the myosin head pulls the actin filament. So that is what is contraction phase. Relaxation phase is word, then again it can't contract, right? That's the relaxation phase. So that is where the you have a thick filament. See, let me draw a Z disc here. Z disc, it's protein. What is it made of? Actinin. Okay. M line, again one more protein. What is it made of? Myomesin. Myomesin and C proteins. Okay. So these are all Z disc. This is M line. This is the thick filament. Okay. So this is, what is this called? Protein component. Tubulin. Thick filament is supported to the Z disc with the help of filament, and it gets attached to the, which helps in attaching the thick filament to the M line, which anchors the thick filament with the Z disc. What is that called? Titin. Very important component in the muscle force production. Remember now, titin. things which are attached to the thick filament? Myosin structure. What is the structure of a myosin? It has a tail, it has a neck, and it has a head. Here you have a myosin ATPase, which helps in detaching, which helps in the power stroke. One is nebulin, which helps in binding the Z protein to the thin filament. Next is actin. Okay, it's a double helical structure. Okay, which has a lot of binding sites, where the myosin has a tendency to bind with that, thus producing contraction. Okay, it has a lot of binding sites, active sites of the actin, where the myosin binds. Okay, what is the third protein? Tropomyosin, which is a rope-like structure surrounding these, which actually protects the binding sites from getting contracted during the resting stage. Okay, and what is the fourth protein? Troponin. So I said troponin has 3 receptors which can link to it. One is troponin C, which has a tendency to get attached to the calcium, and the second one is troponin T, and the other one is troponin I, inhibitory. Yeah, I, inhibitory. Okay, so troponin. Yeah, so these are the 3 receptors, especially this troponin C and troponin T, which has a tendency to get attached to the tropomyosin, is important. Action potential is created at the nerve. So you have resting membrane potential. Okay, do you remember this normal potential, how resting membrane potential is maintained? Sodium potassium pumps, leaky sodium channels and leaky potassium channels. Outflow and 2 potassium inflow. Okay, so thereby it maintains, as well as when threshold potential. So imagine your stimulus is not reaching the threshold stimulus. Okay, so your stimulus is not reaching here, that means you are not producing contraction. Sometimes when the stimulus is good enough, that means it is going to reach the threshold potential, then it goes up, and then ascending limb where the contraction takes place. So what happens during this time? Depolarization. Yeah, your resting membrane potential, which was negative, it is going to become positive now. Yeah, so that is what is action potential, and that potential keep traversing along the nerve. Okay, so let me draw a nerve here, nerve terminal axon. So you give a stimulus, and then action potential is started here, and then normally negative potentials are maintained, RMP. Now because of the action potential, because of the potential which is generated, so what happens? The negative charge is becoming positive charged. So the positive potential, it keeps traversing. So the action potential, it keeps traveling. It is in action. That's what it's called as action potential. And also here you have called as synaptic vesicles here, which you have acetylcholine. There are certain proteins called synaptobrevin, synaptotoxin. Yeah, all those things. It helps in act, and it binds the synaptic vesicles, which has acetylcholine. It binds with choline is released. So this potential, now this is the muscle membrane. Okay, so this potential, what is this called? End plate potential. Okay, so end plate potential. So this is the muscle membrane. Okay, so now nerve is done, coming to the muscle. So now this is the muscle membrane, and what is the muscle membrane called? Sarcolemma. Where is endomysium present? Above that, yeah. So sarcolemma, you have a muscle cell or a muscle fiber, you have sarcolemma here. Okay, so this sarcolemma is a phospholipid bilayer. So this sarcolemma, so I'm just drawing the outer layer of the sarcolemma. It invaginates inside, and that forms, what is that called? T tubules. Okay, and near the T tubules, it is called as a triad. You have something called as, what is this called? Triad. What is the powerhouse where a lot of calcium is stored? Sarcoplasmic reticulum. So these are the sarcoplasmic reticulum. So your end plate potential is created. So the potential is getting transferred to the muscle cell, sarcolemma. So again, muscle cell almost minus 70 millivolt. Again, resting membrane potential is getting changed now. So okay, action potential is traveling. It keeps traveling here too along the tubules. Once this action potential traverses along the T tubules and the sarcolemma, especially near the T tubules where sarcoplasmic reticulum is there, it's going to break open this. Okay. Okay, and then lot of calcium outflow is there. Okay, so lot of calcium outflow is there. Now what happens? Enter the sarcoplasm of the muscle cell. So now imagine this is the myofilaments which are present here. Okay, so now once it enters here, all the calcium enters. This calcium, the troponin has a receptor for the calcium. Okay. So that calcium binds with the troponin part. So the troponin is pulled. It also has attachment to the tropomyosin. So the tropomyosin is pulled. So now the active sites are free so that the myosin head can bind with the active sites. So it goes, attaches, and then that attachment part is called as the latent phase. And then it pulls back. Okay. So now the actin moves towards this side. This actin moves towards this side. Okay. So it comes closer, shortening occurs. Okay, so after that what happens? It goes, for example, it is like this. It goes, attaches, power stroke, it has to detach. That detachment is with the help of the myosin ATPase. Okay, so again detachment, again what will happen? It will have a fresh actin sites to attach. Again it goes, gets attached, does a power stroke, and then it detaches. It's like that. So that's how the contraction takes place. Okay, so once the contraction is done, now the muscle wants to relax. In such case, what happened? Your calcium, whatever is there, it has to go back into the sarcoplasmic reticulum. So there is an inflow of calcium into the sarcoplasmic reticulum. So lack of calcium in this, calcium is reduced here. So automatically, there is the tropomyosin will go and envelop the active sites of the actin. So there is no place for the attachment binding sites, so there is no contraction phase and relaxation phase. This is what occurs during muscle contraction. Clear? Okay, so now coming to this twitch and tetanus. So twitch is only one neural stimuli, so it has the latent phase, contraction phase, and relaxation phase. You know what are the chemical changes that takes place to provide this contraction relaxation phenomena. Okay. Now coming to the tetanus part. So tetanus is, so the neural stimuli, it also depends on, so we said the muscle mechanics depend on the neural stimuli as well as the muscle architecture and the mechanical properties of the muscle. So the neural, so you know what is twitch and this tetanus. How these neural inputs are given to the muscle. There are two factors which determines the graded muscle response. One is frequency of the neural stimuli, how frequently the neural stimuli is provided. The other one is the strength of the neural stimuli. Frequency of the neural stimuli and strength of the neural stimuli. For example, so I will speak about tetanus here. If the frequency is relatively lesser than the frequency of the other stimuli. For example, this is the muscle cell and there is a frequency, there is a neural stimuli 1. Okay, I'll draw a picture. So at this, and there is a second neural stimuli 2. And then this is the third neural stimuli 3, and we are speaking about the frequency, how often it is going to provide. For example, 10 millisecond, 20 millisecond, 30 millisecond, the neural stimuli is provided by the end of the axon terminal. Okay, so one neural stimuli. So this is the first N1, N2 neural stimuli 3 at 10 millisecond, 20 millisecond, 30 millisecond. So what happens is, so this 10 millisecond neural stimuli, it tend to create one. Before it gets down, before it relaxes, if the second stimuli is provided, what will happen? It goes up further. And then before it relaxes, if the third stimuli happens, again it goes up further. This is called as unfused tetanus. So most of our contraction in our day-to-day life activities are based on this unfused tetanus. Okay, now people, that is mainly because of the neural stimuli. If the frequency of the stimuli is okay to this extent, sometimes in such situation, such scenario, where the frequency is which it's provided at a very shorter time. All the contraction phase occur simultaneously and it is fused, and you end up in producing maximal length relationship. And then we'll see about force velocity relationship. Okay, force length relationship. Probably length in that what we are going to deal with is the sarcomere length. That means sarcomere force length relationship. Okay, so if I draw this is the sarcomere length. Okay, so 2.2 to 2.5 almost. Okay, so that should be the optimal length of the sarcomere. Okay, so yeah, sarcomere length. Okay, so this is the sarcomere length. It is in micrometer, and this is the force production. Okay, so it has an ascending limb, and it has a plateau region, and it has a descending limb. So if you see this, when the sarcomere length is very short, when it is almost 1 or 2 or less than 2, so there is from 1 to 2, for example, the length, as the length increases, as the sarcomere length increases, the force production, it keeps increasing, and it reaches the plateau. So the maximum force production you get when the sarcomere length is an optimal length, that is from 2.2 to 2.6, that range. So that is the length of the optimal length of the sarcomere, where you have a maximum force production. Okay, and again, as you lengthen the sarcomere, again it drops down. Okay, so that's the descending limb. So you should have an optimal length of the sarcomere in order to produce maximum force. That is force length relationship. Clear with this? So if you see this, so why does this happen? Why in the optimal length there is maximum force production? Because you just check, number one, during the ascending limb, it is very much shortened. That means it is almost crossing both the myosin, both the actin, it is almost crossing each other. So it has very less sites for the binding to occur. Again, during complete lengthening, you know that there is no very less site for the chances of getting attachments with the actin with the myosin head. So since there is a lack of attachment sites in this and in this, so the muscle won't be able to produce maximum attachment, so no force production. Okay, whereas in the optimal length, you have a good room for maximum attachment to take place. That is why in the optimal length of the sarcomere, you have a maximal force production. Clear? Okay, so force velocity relationship. This, what they have done, they have taken a muscle fiber, they gave stimulus at particular interval. Okay, so here there are a few things which you have to remember in this study. So one is P0. P0 is nothing but the maximal isometric force which can be sustained, which can be produced by that muscle fiber. Okay, so P0 is the maximum isometric force ability of that particular muscle fiber. Okay, so when you give a stimulus, okay, which is more than this, when you give a stimulus which is more than this, and you are giving a stimulus which is less than this, so your force capacity of that muscle fiber, and it also depends on the strength of the stimuli. When the strength of the stimuli is more than the maximal isometric force, you tend to produce a lengthening contraction. That means, for example, you have three factors to remember. Okay, one is isometric force, P0, remember, that is the maximum isometric force with which you can, and the capacity of that maximum isometric force capacity of that muscle fiber, one fiber. Okay, if your stimulus is more than that, okay, then it is going to produce an eccentric contraction. If your stimulus is less than that, then you're going to produce a concentric contraction. So this is basically a single muscle fiber, what they have done from a frog. Okay, so the graph is based on 32 velocity measurements. So they will give a stimulus and then they'll check how the velocity changes with respect to the different stimulus by keeping the isometric. Okay, either they give an increased stimulus or a decreased stimulus than the isometric force. Okay, so first let's take this part, yeah, the concentric contraction. Okay, so what happens as the force decreases, as the isometric force decreases, there is a increase in the velocity. So there is an inverse relationship between force and velocity. Clear? Do you understand? In concentric contraction, there is an inverse relationship. The isometric part, is there any change? There is no change in the force production, is almost similar, and there is no change in the velocity. Concentric contraction, you have to increase the strength of the stimuli. So what happens when you increase the strength of the force, automatically the velocity decreases. Velocity increases, you can produce more force. Okay, so the more the velocity, the more the force production in the initial part of the eccentric phase. This is the force velocity relationship. Getting it? So basically, if this is asked, you have to explain in terms of concentric contraction, then isometric, where there is a plateau, there is not much change between these two form, whereas in eccentric, it forms almost a linear relationship. So inverse, no relationship, linear relationship in eccentric contraction. Architecture of the muscle fiber, which is very important part. So before this, you should have some idea about the Hill's model of muscle orientation. So what is that? Hill's model has a contractile element. Okay, you have a series spring-like structure. Okay, so one is parallel and the other one is series. Have you seen this picture before? So it has two elastic structures. They are the series elastic component and the parallel elastic component, and one contractile component. In terms of muscle, what are these components? Tendon forms a series elastic component which is in line with the muscle. What about this parallel elastic component which is parallel to the muscle? Connective tissues, of the muscle fiber. One muscle fiber is surrounded by endomysium. Okay, so those endomysium, perimysium, epimysium, those are all these parallel elastic components which are in parallel. Do you agree it is in parallel with the muscle fiber? Myofilaments especially. So those are parallel to each other. That's what is called as parallel elastic component. So your muscle force production doesn't depend only on this, but also depends on these elastic components. Okay, just remember. Okay, so now coming to this. Okay, so now here the muscle fibers are arranged in series, and the second one, the muscle fibers are arranged in parallel to each other. It's between in series and in parallel arrangement of the muscle fiber. What is the relation between these two? So architecture of the muscle we are going to see, and in the architecture we are going to see the length, three parameters. Number one, the length of the muscle fiber, okay, and then the width, that is the thickness, and then the angle of pennation. We'll see what is angle of pennation. I'll keep it as beta right now, or theta, whatever you take. Okay, angle of pennation. We'll see what it is. Threes with each other. 1, 2, 3. Okay. So here the change in the length, there will be a change in the length 1 plus change in the length 2 and change in the length 3. So the entire muscle fiber, the entire muscle change in the length is based on the muscle fiber length changes, and each and every muscle fiber, it constitutes that. So you will have a maximum peak length changes. You have to add up all the length changes in the individual muscle fiber, okay, or you can even take it as individual sarcomere, whatever. Now so the length change is maximum here because it is the addition of length changes of the individual muscle fiber which are in series. Okay. Next component, if the muscle fibers are arranged in parallel, means a thicker fiber, this is a longer fiber, this is thicker fiber. So where the force, this will create one force, force 1, force 2 and force 3. So it will be the summation. So peak force will be the summation of F1, F2 and F3. Okay. Whereas the length change will be the average of this length change. Okay. It is not going to, since it is not in series, it is just the average. So length change is not much in this, but force production is good. What about the force production here? The force production is the average of these three. Same thing, because since it is in line with each other. Okay, so the force production is the average here. So what do you understand by this? Here, if the muscle fibers are in series with each other, it can produce a lot of changes in the muscle length and also the velocity of muscle contraction. The velocity with which the muscle contracts can be faster if they are arranged in series with each other, whether the sarcomeres or the muscle fiber. Whereas in case if it is arranged in parallel to each other, the thicker one can't produce faster contraction velocity, okay, but it can produce maximum force. Can it produce maximum force? No, but it can act quickly. Soleus versus sartorius. Where is soleus here? Soleus here. This is soleus. Okay, where is sartorius here? It's here. Both are complete extreme. So he was asking, fiber length you were asking? Okay. So in the sartorius, if you see, the length of the fiber is maximum. Almost, we'll take it as 480. Calculate 480 millimeter. Okay. Whereas in case of soleus, the fiber length is almost, we'll keep it as 25 millimeter. Okay, now I want you to calculate the number of sarcomeres, taking maybe approximately one sarcomere length is 2.2 micrometer. Understood the difference what I am trying to say? Are you understanding? Are you with me now? Okay. So now what I am saying is I am asking you to compare the soleus muscle with the sartorius muscle. Sartorius muscle, it has a longer fiber length. Fiber length is quite long. Whereas the soleus muscle, it has a shorter fiber length. Now I want you to compare how many sarcomeres are present approximately. If you take one sarcomere length is 2.2. Compare and tell me, calculate. So you have 11,000 sarcomeres which are arranged. Okay, in case of soleus, only 11,000. What about this other one? 2 lakhs. So see the difference. So that indicates the muscle fiber length is longer in sartorius, which have lot of sarcomeres which are in line with each other. Whereas in this soleus, very short, very few sarcomeres are present. Compare the plantar flexor and dorsiflexor. Longer, so it can produce maximum force, whereas dorsiflexor can produce, velocity will be more, but the force production is less. Huh? Velocity, contraction velocity, especially shortening contraction velocity, because we are always dealing with the concentrics, shortening. So shortening contraction velocity is maximum in dorsiflexors, but the force production is less, whereas in calf it is opposite. Hamstring and quads. Okay, quads is quite stronger than the hamstring, but the hamstring can produce quick burst of when the velocity is involved, yeah. So they are more prone for injury, hamstring, rather than the quad. Muscles that tend to have a larger cross-sectional area, they tend to have a shorter muscle fibers. His question is answered. So quads versus hamstring, see that number of sarcomeres is quite more in hamstring. That means the fiber length is more. And dorsiflexors versus plantar flexors again. The dorsiflexor weaker than the antagonistic plantar flexors, but it has a greater capacity of change in length and the velocity of shortening contraction. Okay. 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 So now coming to the third part. How does the muscle fiber or the muscle fascicle is oriented with respect to the central tendon? Central tendon in the sense, now you have a tendon here, this is the muscle, you have a central tendon, aponeurosis we say, and how does this muscle fibers are oriented? At a particular angle, isn't it? That particular angle is called as the angle of pennation. Most of our muscle fibers have non-zero angle of pennation. That means it is not at zero. Means very few fibers are parallel to each other, but most of our fibers, muscle fibers, have at least a particular angle of pennation with respect to the central tendon. So these are the fascicles. So the fascicles are at particular angle with respect to the central tendon. That is called as angle of pennation. Okay, how the fibers are oriented. That is basically. So if you see here, you have a multipennate muscle where deltoid muscle, glutes medius muscle, they are multipennate, different angles. You have a fusiform, your biceps is an example. Longitudinal, you have your rectus abdominis. Unipennate, especially the dorsiflexors. Bipennate, especially the rectus femoris. So this will give a better picture. Okay, so unipennate, bipennate, parallel, fusiform, multipennate, circular, convergent. These are the different architecture of the muscle fiber, the design with which the muscle fascicle and the muscle fibers are oriented with respect to the aponeurosis of the central tendon. This is very important in determining the muscle force production, thereby it determines the muscle mechanics. How this is important? What is cross-sectional area? Okay, if you want to find the volume of a particular segment, what will you do? Length, width and height. So that will give you the volume. Okay. So you have area into length. Product of area and the length will give you a volume. Okay, area again. So all length, width and height will give you that. So that is considered as area. Now I want you to say what is area. This, for example, a cross-sectional area, which is nothing but volume of the muscle divided by length of the muscle fiber. Okay. Volume of the muscle and length of the muscle fiber. Most of our fibers have, as I said, non-zero pennation angle. That means you have to consider that also. So what you have to do is, for example, this is the non-pennation angle. You have to measure this fascicle angle with which it is making with the central tendon. So this angle is called as angle of pennation or pennation angle. Understood? So this angle. So when you are measuring the cross-sectional area, you have to consider not only the volume as the length, but you have to consider the angle, cos beta, cos of that particular pennation angle. So this will give you a functional cross-sectional area rather than the anatomical cross-sectional area. Getting it? So this is more important. So question may come, what is functional cross-sectional area? So you should say it is nothing but volume of the muscle divided by length of the muscle fiber or the muscle and into the cos beta, cos of the angle of pennation. So that is the physiological cross-sectional area, which is very important in determining the muscle. Based on this angle variations, when you train, why am I saying this? During resistance training, after resistance training, 6 weeks of resistance training, what are the changes in the angle of pennation we have to see? What are the changes in the neural factors we have to see? What are the changes in the length of the sarcomere we have to see? Is the sarcomere is going to add up in series? Is the sarcomere is going to get add up in parallel? All those things is going to. Those are the factors that is going to determine the muscle mechanics. All those things. So you have to remember each and every factor that is contributing to the muscle mechanics. Now adaptations of these factors with your resistance training we have to discuss in detail. Fiber to muscle length ratio. Okay, this is fiber to muscle length ratio. Understood? For example, sartorius, if you take along the entire length of the muscle, for example, soleus, if you take, fiber to muscle length ratio is very less. So fiber to muscle length ratio ranges from 0.08 to 0.85. That means what? Soleus is very less. So how the fibers are distributed? Whereas the gracilis, sartorius, pectineus, all those things, almost the entire length. The 0.85 means the ratio is 1 is 0.85 means it is close to 1. That means the fiber length and the muscle length is almost similar. But in soleus it is significant difference is there. That means how is it? Angle of pennation is more in case of soleus. Pennation is more. Look at that. Pennation angle is more in the soleus. Whereas the pennation angle is very less in the gracilis, pectineus, sartorius. Suppose you are generating here, it is not directly going to the tendon, but it is also going to the other connective tissues. Okay, so the connective tissues, epimysium, perimysium, all those things are able to transfer. So lateral transmission of force also take place because of the staggered fiber orientation. So it is important to consider the force production from the non-contractile tissue also. Remember that Hill's model? Okay, so that is also important because lateral myofascial force transmission is important. So those connective tissues along with other protein is important in transferring the force from the staggered fibers which are arranged. Okay, just keep it in mind. Only this, isn't it? We just do a force length curve, plateau and this. But because of the presence of involvement of these connective tissues, what you are supposed to do is, and these connective tissues will happen when you get into a lengthened position. So the contribution of the passive elements is also important when you consider the force production. So you must have seen this picture. So the total force is this much. This is the active force. This is the combination of active and the passive force. This is the passive force. Must have seen this diagram. Yeah. So that is the importance of the contractile as well as the perimysium, epimysium, the connective tissues also helps in transferring the force. That's why it is important to consider that force also when you are dealing with the force. As you lengthen, yeah, this comes into play. Because why? They are, very good question. Why it comes in the end range? They are in the, I have written like a spring model, right? Yeah. So it has to get stretched little bit so that it becomes like this to deliver a force. So unless it is stretched, it can't deliver. So it starts to deliver some force only after it gets lengthened to a particular distance. This is the force length curve relationship of a whole muscle. That is the sarcomere force length relationship. So the force production not only depends on the muscle but also depends on the neural inputs. So neural and the muscle. Okay. So the neural, we have seen about the graded muscle response, which depends on the frequency of the neural stimuli and then the strength of the neural stimuli. Okay. And in the muscle, we have two options. Number one, we have seen about the properties, mechanical properties of the individual muscle fiber. Basically, the mechanical properties. Number one is force length relationship of sarcomere. Then we have seen about the force velocity relationship. Okay. Then it also depends on the architecture of the muscle fiber. So the architecture, we have seen about the length. Okay, we have seen about the width, and then we have seen about the angle of pennation. How this architecture is going to influence the mechanical properties we have seen, and all these have to interact with each other. So the interaction of the muscular, neural, everything interact, that determines the muscle mechanics. Okay, thank you.